Hey, this is Mr. Ayton. This is AP Chemistry Unit 9 Review, Applications of Thermodynamics. This is going to be 7 to 9% of the AP exam, and let's get to it. Topic 9.1 is talking about Introduction to Entropy. Entropy is disorder, but on an AP exam, you want to describe it as the particles and their dispersion. If the delta S, the entropy is negative, matter is less dispersed. If the delta S is positive, the entropy is positive, matter is more dispersed. And the first thing you go to is states of matter. You can see water as a solid would have a delta S of negative because it's very ordered. It's not very dispersed. When water's a gas, it's going to be much more dispersed. The entropy is going to be positive. If the states of matter are the same, if you both have gases, go to the number of moles of gas. The more moles of gas, the more dispersion. So you can see 2 moles of NO2 is going to be more dispersion. And then for particle diagrams, just look at the particle diagram. When the matter is in a solid state of matter, it's going to be less dispersed. When it's in a gaseous form, it will be more dispersed. That's topic 9.1. Let's move on to topic 9.2. This is the absolute entropy and entropy change. This is going to use that equation on your equation sheet. Is the delta S of your reaction is adding up all the S's of your products minus all the S's of your reactants. So take a look at this reaction. Let's look at our products. We have 2 moles of POCl3 gas. So you're going to take 2 times 330 minus the total of your reactants. We have 2 PCl3s and we have an oxygen gas. So we would do 2 times 310 plus 1 times 210, and that gives you the delta S, the entropy for the reaction, which is negative 170 joules per mole Kelvin. And why is the delta S negative? Because we're going towards less dispersion of particles. We're going from 3 moles of gas to 2 moles of gas. So that makes sense. Let's move to topic 9.3, which is Gibbs Free Energy and Thermodynamic Favorability. You can use the equation delta G equals the sum of all your G's of your products minus the delta G's of your reactants, just like you did with entropy, just like you did with enthalpy. And it's also using the equation delta G equals delta H, the enthalpy, minus T delta S, the entropy. And so your thermodynamic favorability, if the delta G is positive, it's thermodynamically unfavorable. The reaction's not going to happen unless you provide it with energy. If the delta G is negative, the reaction's going to work. It's going to be a thermodynamically favorable reaction as long as you provide enough activation energy. Which brings us to topic 9.4, thermodynamic and kinetic control. Take a look at this reaction. Our delta H is negative. It's exothermic. Our delta S is positive. We're going towards more dispersion of particles. So when you put negative minus T positive, you're always going to get a delta G of negative, which means the reaction is thermodynamically favorable. But watch out, if the reaction has a high activation energy, look at the potential energy diagram to the right, when the potential energy, the activation energy is so high, the reaction is under what we call kinetic control and won't happen unless that activation energy is provided. Let's take a look at 9.5, which is free energy and equilibrium. Deals with the equation delta G equals negative RT natural log of K. What does this mean is when the delta G is favorable, negative, the K will be really large. And so if you see the reaction to the left, the K is 5.6 times 10 to the 5th, which means the K is very, very big, a lot higher than 1, which means the delta G is going to be negative. The products are going to be favored, and this is a very favorable reaction. Look at the reaction to the right. This is a weak acid. Weak acids don't dissociate, which means the delta G is going to be positive, and the K is going to be much smaller than 1. You'll see in all your Ka reactions, those Ks are very, very small, which means it is a weak acid, it's not favorable, and the reactants are going to be favored. Topic 9.6 is coupled reactions, and you can see in this we have an electrolytic cell, which means this reaction is not going to happen. It's not a thermodynamically favorable reaction. The delta G is positive. Water doesn't break down into hydrogen gas and oxygen gas unless you provide it with electrical energy, and that's why we have a battery provided here. Topic 9.7 is all about reactions that do happen, galvanic cells, or what we call voltaic cells. Voltaic cells, you can take a look. You take a look at your half reactions. You're going to flip the most negative reaction, which means we're going to flip the zinc reaction. The flipped reaction is going to be the oxidized reaction. That's going to happen at the anode. The reaction that you don't flip is reduced. That's going to be at the cathode. You always want to balance the number of electrons. You can see there's 1 electron on top, 2 electrons on bottom. We got to multiply everything by 2 moles. Don't multiply the voltage by 2. And you can add those 2 equations together to get a total voltage of positive 1.56 volts. You can see that because we flipped the zinc half reaction, the zinc electrode is the anode, and oxidation is happening there, which means we're losing electrons. The zinc is quote-unquote losing mass, which means the zinc solid is dissolving and becoming more and more zinc plus 2. We start with 1 molar of zinc plus 2, but we're getting more and more concentrated for our zinc, which means the NO3 minus, to keep electrical conductivity, the salt bridge, the nitrate, is going to migrate that way. On the other side, we have the cathode. The cathode is reduction, which means we're gaining electrons or we're gaining mass. The silver ions in the solution, the 1 molar, are going down, 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 and we are plating on silver solid, which means since we're losing the positive silver ions to become solid silver, that's where that mass is coming from, the sodium ions are going to migrate that way from the salt bridge. And the electrons always travel from the anode to the cathode. Well, topic 9.8 is about cell potential and free energy. That's delta G equals negative NFE. If the delta G is positive, that means the E is negative. This is an electrolytic cell. You need a battery because that's thermodynamically unfavorable. If the delta G is negative, the E is positive, and that is a galvanic or a voltaic cell. That's what we just took a look at. That's going to generate energy, and that's thermodynamically favorable. Whenever you're going to do this equation, you have delta G equals negative NFE. The negative N, the N means the number of electrons that you transferred. Take a look at this reaction. We have 2 electrons and 3 electrons. The common number is 6 electrons transferred. The F is Faraday's constant. That's on your equation sheet. That's 96,485. And the E from this reaction, when we added it up, was positive 0.90 volts. You multiply all 3 things together, and we end up getting a delta G of negative 521,000 joules per mole, which you can change to negative 521 kilojoules per mole. Since it's negative, negative for delta G, that reaction is thermodynamically favorable. Let's take a look at topic 9.9. This is when we're non-standard conditions. This uses this equation called the Nernst equation. You can see the E, the standard cell potential, the E with that little degree symbol, is positive 0.32 volts. That's what it should be if you had 1 molar of zinc ions and 1 molar of iron ions in your little electrolytic cell. But what happens if the E of the cell is measured to be positive 0.42 volts of electricity? You're getting more voltage of electricity, which means your reaction is getting more favored. It's pushing to the right-hand side, which means the Q is less than the K, which means the iron ions have more concentration than the zinc ions. Well, if that happens when we're getting more voltage, if we get less voltage, that must mean the complete opposite. The Q is going to be greater than the K, which means the zinc ions are going to be greater in concentration than 1 molar. The iron ions are going to be less than that 1 molar. And last but not least, we have topic 9.10, which is electrolysis and Faraday's law. That uses the equation on your equation sheet. I equals Q over T. I is the amps, T is the time in seconds, Q is the charge. So if we were given 0.8 amps for 1800 seconds, we multiply that to find our Q, or our charge. Our charge here, if you do that on your calculator, is 1440 coulombs. Then we're going to set up a proportion using that Faraday's constant. 96,485 coulombs for every 1 mole of electrons. We know we have 1440 coulombs. We can find out the moles of electrons. There is 0.0149 moles of electrons. And since for every 1 mole of electron transferred, there's 1 silver ions, you can see silver is +1, then we know we have 0.0149 moles of silver. We can multiply that by the molar mass, and we get 1.61 grams of silver that's plated. And that is a quick review of Unit 9, Applications of Thermodynamics. This is Mr. Ayton, signing off.